Nice to have Richard Easther begin this morning session to tell us about early universe scenarios. Please go ahead, Richard.
So thank you very much for inviting me. I have to say, when I saw that this was kicking off, or that this group was getting together, I was really, I did feel sad that I couldn't make it to the workshop. But it's something that it's very much an idea, and idea whose time has come, I think, and it's something that's been sort of ticking away in the sort of various activities that I've been involved with for a long time. So I should acknowledge at the outset here, I've worked with closely with Eugene Lim on this over the years. My first PhD student, Tom Giblin, we did a lot of work together on this. Also, another student of mine, Hal Finkel, and I've collaborated with Ed Copeland on some of this work as well. What I plan to do today is to give a fairly broad and kind of conceptual overview of what the sources might be. I was actually really fascinated to hear some of the discussion earlier about, the value of having a clear, theoretical prior to go after. What is the idea that would make theorists the most miserable, if we weren't able to verify it. But I think there's also value here in the sense that, as I'm going to say, there's an opportunity in some sense to do a blind search for new physics above the TeV scale. And so I want to sketch out some broad conceptual thoughts about the way that the state of cosmology and the things that we don't know about the universe at the moment, and also then focus a little bit on various specific mechanisms that can drive the production of high frequency gravitational waves in the early universe. Also, just want to note that I am in New Zealand, and so I mean, COVID is in many ways a terrible thing, but the ability to participate in meetings in Europe during what would be teaching time for me. So even if I had, even if without COVID, I wouldn't be able to attend in person at the moment. And we're also saving about 7 tons of carbon by having me arrive on Zoom. So the opening thoughts of this, when I say early universe, I've sort of excluded the electroweak phase transition, although that's not strictly speaking a high frequency. It's high frequency at production. It's not high frequency at time of observation. So I'm thinking in terms of things that involve temperatures in excess of 1 TeV as a reasonable benchmark. And so physics beyond the reach of the LHC, some things that are outside of the standard model, or various low energy extensions that you might be able to smuggle into it. So I think it's important to note that as soon as we start talking about this, we're playing for high stakes. We're talking about physics that we don't understand. So whatever you can discover beyond the standard model is going to make people enormously happy, just given in direct proportion to the success of the standard model up until the present day. And the other thing, of course, is that this is, we understand the early universe back as far as maybe neutrino decoupling, because that happens at a somewhat higher temperature than nuclear synthesis. And we've seen evidence for a cosmological neutrino background in various ways. But there's a big chunk of the early universe that's essentially unexplored. And so we're really playing for, whatever mechanism that produces gravitational waves in the early universe would tell us both immediately something radical about the early universe, in the sense that we don't know of any, nothing in the standard model of cosmology needs to produce a substantial gravitational wave background at high frequencies. And likewise, would be telling us things about physics that were not currently understood. So I mean, in terms of the potential impact of this field, I mean, obviously I'm preaching to the choir here, but it really strikes me as an opportunity to do two quite radically interesting things at the same time. I'm going to try and distinguish between what we think and what we know when I give this presentation, just because, particularly when you get a group of early universe cosmologists together, we're used to working on ideas that seem plausible and seem reasonable simply because a lot of our colleagues are working on them. And it's actually very hard to develop, independent, rigorous quantitative priors for the likelihood of theories that lie well beyond the range of any other physics experimentation that we've been able to do. And so it's probably important to keep those things in mind as we develop, or as a group of people is developing proposals to test some of these ideas to explore this unknown patch of the universe. So in terms of an example of what we think, rather than what we necessarily know, this is an example of the so-called, the funnel diagram, as it's sometimes known, that was produced by WMAP. And it's a beautiful explanation of, the standard model of cosmology. It has in it, everything from the dark energy, the evolution of cosmic structure. So you go through a dark age after the microwave background has essentially been able to move freely through the universe. But before the first stars turn on, you produce a whole bunch of small galaxies. They undergo a series of mergers to produce large galaxies, and eventually also you see the impact of dark energy kicking in. In the early universe, they've painted they've posited the period of inflation, which has the job of essentially fixing the initial conditions. You have whatever mechanism corresponds to the Big Bang, you have this period of accelerated expansion that both wipes out any memory of the very early universe, and also at the same time is able to imprint on the early universe a set of density perturbations that are capable of seeding both the irregularities that we see in the microwave background, and also providing the initial conditions that lead to the collapse of overdense regions in the early universe that leads eventually to the formation of galaxies. So this is the so-called standard model of cosmology, with the exception of arguments at the moment around whether or not the value of Hubble's constant measured in the local universe with reference to things here as opposed to things that reach back here. We get two different numbers for that, and so there's arguments raging in the field as to whether that's some systematic error is involved, or whether there's really new physics between here and here that might be changing, that might need to be added to this diagram. But by and large, this represents the consensus among cosmologists as to how the universe has evolved since the Big Bang. But if we want to go back to things that we can be more confident that we know, it's worth reflecting on why it is that we think that we need an inflationary phase in the universe. So I'm going to take statements about general relativity, or about the predictions of general relativity, and assumptions about causality. I think those are relatively safe to say that those are the things that we know if we had a meeting about gravitational waves. But one way to explain the need for inflation in the universe is to note that the universe today is about 40 billion light years in radius, the visible universe. And the reason that's different from the age of the universe is that the distant parts of the universe have receded from us since light was emitted from those regions. And so we get about a factor of 3 that comes out of the map when we do that. That's about 2 × 10⁻61 Planck lengths. And so that tells us that if we take a patch of the early universe and we expand it by a factor of 10⁻60, and so if we assume that the Big Bang was some process that produces, quantum-y space-time, then there's a minimum amount of growth that we've needed since that point is this factor of 10⁻60 that would get the universe up to the size that we see it today. So the scale factor is the function from the metric of space-time that describes the expansion of the universe. And so one way of stating that is to say that, whatever the scale factor is today, because it's typically a free parameter and a free multiplicative parameter, if we made it 10⁻60 times smaller, then we would be back at the point where everything in the universe today would be sort of contained in one tiny little volume of quantum foam. On the other hand, if we make the same argument about the present day temperature of the universe, and so we look at the microwave background, which is 2.7 kelvins, that's about 6 × 10⁻⁴ electron volts. And we remember, of course, that the Planck scale is 10⁻19 GeV, or about 10 to the 28 electron volts. We remember too that the temperature of a black body scales in inverse proportion to the volume that it's inside. Ultimately, it's just that the photons in the microwave background are redshifted by the expansion of the universe. The temperature and the wavelength of the peak of the black body spectrum are inversely correlated. So when the universe is 1,000 times smaller, it's 1,000 times hotter. To get back to the Planck scale or the Planck temperature, we only have to go back a factor of 10 to the 30 rather than a factor of 10 to the 60. And the mismatch between those two numbers there's another way of stating the kind of difficulties of conventional cosmology that motivate the need for inflation. And so we're left now, that's stuff that I think we can safely say that we know, but we're left now with the stuff that we think. And the stuff that we think is that we have, if we look at this as the kind of logarithmic expansion of the universe, so the universe has grown by about a factor of 10 to the 10 to the 12, 10 to the 15, maybe since the temperature was at the TeV scale. So you take TeV scale temperatures, you make the universe 10 to the 15 times larger, you get down to a fraction of an electron volt, which is what we see today. It's obviously a very hand-wavy number because I'm not taking into account the changing number of degrees of freedom or various other ways of reheating the microwave background. But roughly speaking, everything that we see in the universe or everything that we understand happening in the universe has happened in a time in which the universe is expanded by a factor of maybe 10 to the 15, probably a little less. That leaves us with another 10 to the 15 worth of expansion that takes place in what is sometimes called the Dark Ages or the primordial Dark Age. And that's a term that's used by Boyle and Steinhardt. They're not talking about the Dark Age before the stars turn on. They're talking about the Dark Age when the universe doesn't need to be inflating, but also that it's governed by physics at scales or energies that are well beyond, beyond the reach of the LHC. And then we have at least 10 to the 30, but potentially much more worth of expansion during the inflationary phase. And so the picture that you get from this is that the first 45, 10 to the 45 worth of growth undergone by the universe, this takes about a trillionth of a second in the conventional cosmology. And in everything else, everything that we care about in the universe, all of the stars, the planets, the people, the formation of atoms, that all takes place in this last little box here, and obviously in 10 to the 13.8 billion years, minus a trillionth of a second. So, depending on how we slice up the timescales here, we get very different pictures of, whether most of the universe correspond, or that the lifetime of the universe measured in terms of, logarithmic expansion happens at energy scales where we don't understand the physics, whereas everything subsequent to that is this piece that's added on to the almost not quite an afterthought, but the last quarter of the growth of the universe if we're measuring that logarithmically. So there's plenty of scope for interesting, the point of this really is that there's plenty of scope for interesting things to happen in the early universe, both in terms of the number of decades that we can increase the typical interaction energy by before we reach, running out of where we think we understand physics, but before we reach the Planck scale. And also in terms of the number of, Hubble times, the number of doubling times that the universe has undergone. So inside of this context, the other statement or statements that we can make is we know two categories of mechanism that can produce gravitational waves. One of those categories is quantum mechanical. And by quantum mechanical, I mean mechanisms that would not work if h bar, if Planck's constant was exactly 0. And so those mechanisms include, or the most obvious mechanism there is simply the inflationary gravitational wave background. And so my guess is also that the inflationary gravitational wave background, even though it's it's a critical concern to people doing large-scale, measurements of the microwave background, it's also probably the mechanism that will be of the least interest to a meeting like this. And so we have fairly clear physics that the wavelength of formation is proportional to the Hubble scale that exists at the time, which goes or scales inversely with the density of the universe. So it's not there's a power in there, and there's a power relationship in there as well. It's a Hubble squared is equal to rho, and rho is equal to the energy to the fourth. But roughly speaking, the Hubble scale is a constant or very slowly decreasing during inflation. And so that means that because the amplitude of creation is relatively constant, but because the waves then move outside of the cosmological horizon, or the Hubble horizon, at which point their amplitude stays relatively fixed, It's stretched by the subsequent expansion of the universe, but their amplitude is not redshifted, which would be the case if they were propagating inside of the horizon. So this produces this very flat perturbation spectrum with this very slight red tilt for typical inflationary models that very large class of inflationary models that operate in the early universe. So those gravitational waves exist at all frequencies from scale wavelengths from microwave background scales today to scales that would be relevant to a tabletop experiment. But the amplitude of this signal, because it exists at all frequencies, if you were to measure it in the microwave background, the most logical other place to go and look for it would be at solar system scales, things like the SIGO or Big Bang Explorer, things that are between somewhat shorter wavelengths than LISA. It's not necessarily something that you would want to chase after with an experiment that was focused on frequencies at megahertz scales and above. The other thing is that as the amplitude is constant while super horizon, these things re-enter the horizon and then scale like radiation. So they're present on all scales, but as I said, probably not motivating experiments like the ones that you're talking about. It is worth noting that things like ekpyrosis or proposals that suggest that the universe, the initial conditions for the universe is set during a contracting phase, followed by a bounce, followed by re-expansion. In those scenarios, the gravitational waves, if they're produced during their contracting phase, the Hubble constant during that time, the density is going up. The Hubble length is 1/h is going down. And in those scenarios, you're actually going to produce a gravitational wave background that is shorter and more visible at short wavelengths than it is at long wavelengths. So potentially more relevant to not to tabletop, but to high frequency experiments that might conceivably be done. It's worth noting that there was news this month that the cosmological background had been better constrained thanks to the work of Bicep and Keck. So really starting to see that the typical models of inflation that you learned about in grad school 10 years ago, 20 years ago, 30 years ago, almost all of those models are ruled out. You can also produce, quantum mechanically, you can produce gravitational waves through Hawking radiation if you have decaying primordial black holes. This is something that I worked on about a dozen years ago, also Dogov and others have papers on this. So you can get a very, very high frequency spectrum up to 10 to the 18 or 10 to the 22 hertz. Not an insignificant amplitude in some cases, but I'm going to move on from there just to mention the existence of that as a possibility. But again, in the quantum mechanical category. On the other hand, the other way to produce gravitational waves is just by accelerating material. And so that may still be a quantum source, maybe a phase transition or quantum materials, string networks. But you're producing the gravitational waves through the parts of the appropriate parts of the Einstein equations, sourced by the transverse traceless parts of T mu nu. So that will still be, that has to happen in the post-inflationary universe in order to be observable, because if not, inflation will wipe them away. It will also be associated with periods of high inhomogeneity in that phase, in that primordial dark age where we don't understand what's going on. There's plenty of scope for this, and typically on scales that are much smaller than present day cosmological structure. So one of the things we know is that if inflation happens at all, it must come to an end at some point. Otherwise, the universe would still be inflating. Post-inflation, typically the universe is filled with a cold, coherent inflaton condensate that's sloshing around in the bottom of its potential. And so some mechanism must thermalize the universe. There's many mechanisms that can do that. One of which is that you resonantly produce inflaton quanta off this condensate. Other mechanisms where you produce scalar particles that are coupled to the inflaton, or spin, particles with finite spin that are coupled to the inflaton that tend to have different production mechanisms, or no resonant production of anything, and somehow you have to do this through perturbative channels. Because the mechanism of inflation is unclear, The mechanism of that couples the inflaton to standard model particles to produce a hot Big Bang is in some sense doubly unclear. You can write down a working inflationary model without having to worry about how that it thermalizes. And you say, well, now I've got to couple this to the standard model in some way. And I don't know what that is. So this is both of these things are unknown. Even if we believe that inflation happens, we have very little clue as to what the reheating mechanism, the thermalization mechanism might be. One mechanism to do that is this so-called parametric resonance, where you have essentially individual momentum modes of fields that are coupled to this oscillating quantum condensate are resonantly produced. So you have an exponentially rising occupation number. In these cases, you can reasonably quickly drain the energy out of the inflaton field and convert them into quanta of the inflaton itself or of other fields. And when that happens, the universe is highly inhomogeneous, and you have all the circumstances you need to produce a gravitational wave background. So I have this visualization here. This is the scaled inflaton. So it's a physical slice through space, and the direction here is the value of the field. And you can see that it generates, if you start off with almost invisible perturbations in this field, it generates relatively large perturbations in this field that's coupled to it. Those then back react on the inflaton field, and you produce a highly inhomogeneous universe. So we can look at that, and we can look at the gravitational wave production during this phase. So this plot was made by Tom Giblin, good enough to share it with me. So this is the same thing that we saw previously. And what we're seeing here is the spectrum of gravitational waves that would exist in the present day universe. So the frequency of production is orders of magnitude higher. This corresponds to the present day frequency of gravitational waves. And you see that there's this fairly typical tail off at long frequencies, and then typically a cutoff, that a steeper fall off that happens at high frequencies. And so this particular signal is peaked at about 10 to the 8, 10 to the 7 hertz. And for this particular scenario, we're looking at something that's probably, I think, has a peak of h squared omega GW of around, I'm just reading it off this actually, maybe 10 to the minus 11. So not a much bigger signal than we get from a much bigger signal than we get from the stochastic background that's generated during inflation, but not necessarily as huge as some other stronger mechanisms. So this, just want to cite the people who originally drew attention to this idea, to the best of my knowledge, Klebnikov and Kachev in this paper from 1997. And then there was a kind of sort of a decade later, a bunch of people returned to this. Myself, Tom Giblin, Eugene Lim, Hal Finkel, and others working with me. Juan, Danny, and others were sort of part of the competition on this. And then also a group that was centered around CEDAR, I guess. Lev Kaufman, obviously, Dick Bond, Gary Felder, and Defoe. So there was a sudden kind of, sort of this sort of was there and known about for a while, and then sort of 15 years ago, this topic was picked up by a number of people. The interesting thing about this mechanism is because it's a causal mechanism, when the gravitational waves are produced, their wavelength has to be small enough to fit inside of the Hubble horizon at the time. The size of the Hubble horizon scales inversely with the density of the universe, or the density, the square root of the density of the universe, or the square of the typical energy. So as the universe grows, or at lower energies, you can produce a longer gravitational wave. On the other hand, the gravitational waves produced at very high energies, the universe has grown more since that point, which redshifts them to a lower frequency. But the combination of things is such that the lower the energy of the universe, or energy density of the universe at the time at which resonance takes place, the longer the wavelength of gravitational waves that you can produce at that time. Although there's no guarantee that the mechanism of resonance is going to produce gravitational waves that are in any way comparable to the current Hubble length. So some of this is laid out in a paper that Eugene and I wrote in 2006, and I was looking at it as I prepared this talk, and we were talking about the possibility that we could produce gravitational waves in the early universe. And we have this quote from 2006. We believe that the time is right for revisiting this question. So clearly, if it was ripe in 2006, it's very ripe today. I just want to make some observations about this. Production, as I said, production at lower energy means that the gravitational wave background can be at lower present day frequencies, but typically from the LIGO bound would correspond, or LIGO range would correspond to relatively low scale inflation relative to where inflation can happen. The gravitational wave spectrum reflects, in some sense, the detailed mechanism of resonance. There are many possible mechanisms of resonance. The particular modes that get excited will depend on that mechanism. And so the shape of the spectrum carries information about the physics of the resonant area. And that's in contrast to the inflationary background, the quantum background, which is which is sort of almost by design. Its main feature is that it's going to be featureless. The reheating history has an unknown impact on the signal, which is not necessarily talked about in a lot of detail. You can go through resonance and still be matter dominated and then have to thermalize at some later point. So the gravitational wave energy density will be diluted until thermalization happens, because this is effectively a component of dark radiation that's living inside of a matter dominated universe. And so this is the theoretical uncertainty that goes into any of these calculations, unless you also have a mechanism that describes the thermalization of the universe as part of your resonance process, as part of the resonant process. I haven't talked about oscillon production. These are long-lived inflaton-bound states. Essentially, they're produced by nonlinear physics inside of the field theory, inside of the Klein-Gordon equation. They're not, strictly speaking, gravitational phenomena. Their production is associated themselves with a distinct gravitational wave spectrum. So that's, again, something that that is able to be investigated and uncovered. The last thing that I want to talk about, I'm just mindful of the time here, is that there is the possibility of having a very long period of matter domination post-inflation. And so one of the things that we've realized more recently is that if you don't have resonance, you just have this sloshing inflaton background, what you have is a self-gravitating quantum condensate. And its simplest limit, it's actually described by the Schrodinger Poisson equation. You can turn on self-interactions and you get the Gross-Podevsky equation. But it's effectively a WKB approximation to the Klein-Gordon equation, and it operates in a non-relativistic limit of the Klein-Gordon equation with local gravity. It's a very trendy equation because it describes ultralight or fuzzy dark matter or axion dark matter. These are typically very lightweight axions, 10 to the minus 21 electron volts typically, which puts your Compton wavelength out on kiloparsec scales. And so there's been a fair bit of effort devoted to understanding the astrophysical implications of this kind of dark matter. And that's prompted the development of solvers that will solve for the dynamics of something that on the one hand obeys the Schrodinger equation, but on the other hand feels the potential that's coming from its own local gravitational potential, which is sourced by by psi squared, the square of the wave function, which is obviously proportional to the density. So this would apply in the absence of resonance. If you have strong resonance, then you need to revisit some of these assumptions because that can produce relativistic quanta. But it produces a matter-dominated phase that's analogous to present-day structure formation. It can actually last much longer because present-day structure formation is only 2, 3, or 4. The universe has grown by a factor of maybe 10 to the 3, 10 to the 4 since matter radiation equality, 10 to the 4 since matter radiation equality, 10 to the 3 since the CMB decoupled. Whereas in this case, the universe can grow 10 to the 12, 10 to the 13 times larger. So you can go much deeper into a matter-dominated phase than in the one that we're living in, or were living in recently, until the dark energy turned on. You can convert existing tools and techniques. So pressure sector, N-body calculations can apply equally well, almost as well in the early universe as they do today. And so this is something that I developed, or something that I noticed first was my postdoc, Sean Hotchkiss, and Nathan Masoki, who was a PhD student with me in Auckland, is now working in the United States. And so we've developed this, or we've been developing these calculations over the last year or so. Got another paper coming out on this next week, but looking trying to quantify in some detail the kinds of inhomogeneity that can happen in a matter-dominated phase that follows inflation, where the thermalization is slow and resonance, on the other hand, has not, for whatever reason, taken place. I just want to say that there's a lot of scope for interesting physics. We're looking at this and realizing that there's a whole playground that's never really been explored, that describes this long phase, and many of these possible scenarios could lead to gravitational wave production by a variety of mechanisms. I just want to throw this in. This is becomes from what we think is the smallest scale simulation of nonlinear gravitational physics in the early universe. This is a blob of inflaton matter that's collapsed. The universe has grown by a factor of about 10 to the 20 since the end of inflation. And this blob of matter weighs about 20 kilograms, about as much as a medium-sized dog, but it's about 10 to the minus 20 meters across. And we've been able to follow this in some detail in our simulations. So just an advertisement for that. There's also the possibility, or not the possibility, the reality, during a phase of extended matter domination, you can produce gravitational waves via second order effects. Those will be high frequency still if you map them into the present universe, but also their amplitude is dominated. If they're produced early in the matter dominated phase, their amplitude will be diluted until the point where the universe thermalizes, which is an unknown time. You can put a lower bound on that time, but you don't necessarily know when that is. So the spectrum of the gravitational waves that you produce, or that you were to see today, would also be convolved with the subsequent expansion history of the universe. We've made no mention so far of what happens when we put gauge fields or phase transitions. Inflaton is presumably coupled to other fields. There's a potential for having more complex dynamics in this transient phase, and we do know, for instance, that we can get gravitational waves coming obviously from phase transition or from transient networks of topological defects. And as I said, the thermalization mechanism, whatever it might be, whether you have resonance or not, in most cases the detailed thermalization mechanism is not 100% clear. So to wrap up, I think there are many, these questions in many cases have been looked at for decades. They're not necessarily new problems for the community. They're familiar topics. The high frequency gravitational wave bounds on these things are really blind searches for new physics. There's a vast number of possible production mechanisms that could operate in the early universe. And you could argue that going to look for a gravitational wave background is potentially cheaper than building a bigger particle accelerator. Whether that's a tactful thing to say in Geneva or not, I'm not 100% sure. I think it's worth pointing out that the priors on the plausibility of theoretical ideas are very difficult to quantify. Applying pure reason to the world did not work especially well for the classical Greeks, or at least for Aristotle. But we get gravitation, but we do know that we get a gravitational wave production, through resonance in quite simple inflationary models. We don't have to add new or additional physics to very simple inflationary models in order to produce the possibility that you get a resonant production of firstly resonance, and the resonance is typically associated with gravitational wave production. So it's clear that we're not inventing models that produce gravitational waves so that we can then pretend to test them. We've got models, we find out they produce gravitational waves, and then we would very much like to be able to test those scenarios. The long matter-dominated phase, that shows up in quadratic inflation, a model that was written down, I think for the first time in 1983, maybe. So it has a vast range of possible consequences, and those have not been explored in their full detail, even up to the present day. Although we're closing in on some of those with this Schrodinger-Poisson analysis. But again, this is a model that's really close to 40 years old at this point, but its physical consequences in the nonlinear phase that can follow it have not been explored in detail. If you have quick thermalization, I think it's hard to imagine how that happens without some sort of resonant mechanism. If that does happen, it also will preserve the gravitational wave amplitude, even if it means that you can't have interesting physics during this matter-dominated phase. The inflationary resonance has this nice inverse correlation with inflationary scale, and that as you move the inflationary scale to lower energies, then you have the possibility, although not the requirement, that you can produce lower frequency gravitational waves through this resonant signal. It also looks, hang on a minute, I've missed out a knot in this thing. It looks as though if inflation did happen, it did not produce a large stochastic gravitational wave background. So there is a strong scaling of amplitude with inflationary scale. Whether or not it is natural for inflation to produce a large stochastic gravitational wave background is something that really is a topic of heated debate inside of the theory community. There's two fairly polarized sets of opinion. And there's also a tendency, I think, by the experimental community to listen more carefully to theoretical colleagues who are likely to say that yes, inflation needs to produce a large gravitational wave, quantum background, because that then obviously provides better motivation for experimental searches. My own feeling is that I'm much more agnostic as to the value that this should take. I don't claim to have deep insight into this. I think the fact that you could put tight bounds on that quantity, it rules out large classes of inflationary model. I think that's useful and informative. But I wouldn't want to pick a particular side in the argument as to whether this was something that inflation was required to do. Or I guess by doing that, I'm picking the side that says that inflation doesn't in fact need to do that. I don't think the consequences of the fact that the shape of the inflaton potential has been fairly tightly constrained by experiments by BICEP2. Even if you were to detect a gravitational wave background at something close to the bound that BICEP2 is currently, the BICEP2 Keck measurements are currently suggesting, then that rules out basically all of the models that people were playing with, a dozen years ago, or at least the simple ones. And so the consequence of that is I don't think we've necessarily fully thought through what that might be telling us about the mechanisms for resonance, for instance. Is definitely things to learn there that we haven't thought about, and that could have priors on the gravitational wave background that would be produced through resonance or through nonlinear effects after the end of inflation. And so that finishes up my talk. I hope I haven't gone heinously over time or eaten too much of the discussion time. I won't be around for the early morning discussion session, but I will try to make sure that I can correlate my schedule with the chat tomorrow morning Geneva time. Thank you very much.
So thank you, Richard. So in fact, you did actually go 15 minutes over the.
Oh my God! I'm so sorry.
No, it's okay. So what I'll say is that we'll take one question, and I mean you raised a lot of things. Thank you very much for that really nice and really overarching review. So maybe if you have further questions that we can continue them over Mattermost. So I actually saw Andreas's hand first, but it was then put down. Andreas, did you have a question?
No, I will contact Richard.
Okay. So Juan, do you want to ask a question?
Actually, more than a question, it's a comment. I'd like to side up with what you said about whether inflation predicts or not a measurable stochastic gravitational wave background from quantum fluctuations. Now, we know Stravinsky models, which also range from those 40 years ago, right, predicted a very tiny amplitude of the gravitational wave background. But there are other models like Higgs inflation, where we know we're using a scalar field that we know exists, right? We don't have to add anything new to it. Inevitably, even if you don't put a nonlinear coupling to it, it will raise it through radiative correction. So it's natural to expect that something like the Higgs could have been out there even producing inflation. In that case, R is 10 to the minus 3, few 10 to the minus 3. So it's natural that the BISAP should not see it. So from that theoretical bias, I would argue nothing wrong with the BISAP Keck measurement. And that was
I agree. I'm not, I mean, there are people who kind of nailed their colors to R greater than 0.1 or something, you know, who you know.
But we knew this 40 years ago. That wasn't anything.
I think we did, but I mean, there have been. I mean, all I'm saying is that there are people who build those experiments. I mean, it could equally well be that R is 10 to the minus 20. I mean, that there are plenty of models that will do that for you. And in that case,
I wouldn't go that far. But one thing is the science, and the other one is how you get the money to get your experiment. And I guess if you want to ask for support to NSF, you have to say, I'm around the corner of discovering the gravitational wave background, the B modes, right? So you say it's going to be 0.1, 0.2, 0.3. But of course, there are models that would agree with that. But if you find that it's below, say, 0.06, then fair enough. We're just exploring a different range of models. That's it.
No, I think I agree. I think one thing that you can know is that once you have that constraint on the model space, then the possible, you know, that does tell you something about the shape of the inflaton potential as you come in towards the center. And I think there probably are not, I mean, you can never draw fully generic conclusions, but I think there probably are things to learn about the possible resonant mechanisms that would apply in typical models of that form. Once you start getting complicated couplings to gravity and stuff like that, then maybe you've got a larger parameter space and you have to be a little bit more careful about what you're saying. But I think there are conclusions that can be drawn, and I don't think we have yet drawn them, I guess is what I would say, but would definitely have a bearing on the kind of motivation that you would find for going and looking for a preheating signal and
definitely with the Higgs as an inflaton, you open a new avenue, which is the production of gauge fields, fermions, etc., much beyond what you have in Stravinsky type models of inflation. So the reheating part is completely different, even though the measurement of the R factor, the tensor to scalar ratio, is the same. You still have a completely different phenomenology. So you open up a window rather than closing it.
Yeah. Well, my apologies for eating the time, guys. I'm really sorry.
It was an interesting talk, and it was. I should have actually prompted you before, but no, it was.
Thank you for taking the blame, Sabota. I appreciate it.
It was a real pleasure to hear all that. So maybe Geraldine, I can get you to start sharing your slides.